Today we're going to talk about something called Hess's law. So the release or absorption of heat energy is actually a unique value for every reaction. Sometimes it is not easy to measure directly for certain reactions. And so what we find is that if a reaction is carried out in a series of steps, we can often find the enthalpy change for the overall reaction by sum or adding together, finding the sum of the enthalpy changes for the individual steps. Here's an enthalpy diagram so you can kind of see what I'm talking about. If we look at the combustion of methane gas forming CO2 and H2O, what we find is we can actually do this reaction, or this reaction can occur in two individual steps. The first step, which is going from methane and oxygen gas to carbon monoxide, water, and oxygen gas, produces 607 kilojoules of heat. Continuing from this carbon monoxide, water, and oxygen gas onto the products down here, CO2 and H2O, produces another 283 kilojoules of heat. So these two individual steps, if I take the enthalpies and add them together or sum them, I actually get the overall enthalpy change for the reaction. And that's really what Hess's law is all about. Let's take a look at an example. The goal of Hess's law is to try to find the enthalpy for a reaction that maybe might not be easy to find. So what we do is we find two reactions that at least contain some of the same reactants and products of the reaction that we're looking for. What we're going to look for is we're going to look for the reactants first, and we see carbon is on the reactant side and so is oxygen. So what I like about this first reaction is it also has carbon and oxygen on the reactant side. So I'm actually just going to carry that reaction right down as is. The second reaction, however, has carbon monoxide on the reactant side, and I actually want it to be on the product side. So I'm going to reverse this reaction and carry that reaction down. So remember, when we reverse the reaction, that actually changes the sign of enthalpy. So we'll check that out here in a second. But the premise of Hess's law is that we start canceling out things that show up on both the reactant and the product side. So for example, carbon dioxide shows up on both the product and the reactant side, which really means it gets produced in one area and used up in the other. If we take a look at oxygen, I can see I have half a mole of oxygen on the product side, but a full mole on the reactant side. So I'm actually just going to cancel out half of a mole of this oxygen on the reactant side, and so that leaves me with 1/2 mole. Now, if I bring this down all together, I find that I have 1 mole of solid carbon, which is probably graphite, and I end up with 1/2 of a mole of oxygen gas. And I'm producing, on my product side, 1 mole of carbon monoxide gas. And this directly matches up with the reaction that we're looking for. So it's kind of like a puzzle. You're going to flip, you're going to multiply, you're going to change signs to try to come up with the overall reaction. Keep in mind, the final delta H is the sum of those two reactions. So you can see we ended up with negative 110.5 kilojoules, because what happens is I end up taking the negative 393.5 kilojoules and adding that to a positive 283.0 kilojoules to get negative 110. So some things we need to keep in mind for Hess's law. If a reaction needs to be multiplied by a coefficient, then we're going to multiply delta H by that coefficient. So for example, if we double the coefficients, the enthalpy of a reaction is going to change. It's going to change by a magnitude of 2, or it's going to double. If we have to triple the coefficients of a reaction, delta H is going to triple. If we cut the coefficients in half, we have to actually cut the enthalpy of reaction in half. If a reaction is reversed, the sign for enthalpy also changes. So if it's originally exothermic and we flip the reaction, it now becomes endothermic and vice versa. Also, Hess's law can be represented using enthalpy diagrams like the example I just showed you. So kind of keep that in mind because you may have to write enthalpy diagrams for these reactions. Let's take a look at one more example. The example we have actually has 3 individual steps, and I'm going to try to make all 3 of these individual steps somehow come together to get my overall reaction of taking graphite, reacting it with hydrogen gas to produce C2H2 gas. So let's take a look at a couple different things. First of all, I have C2H2 on the reactant side, and up here in the first reaction, it's on the product side. So the first thing I'm going to do is I'm actually going to flip that reaction. So let's rewrite that. Reverse. So we're going to have H2O liquid, and physical states are important too because sometimes you may have different physical states for the same substance, so you just have to be careful. So 2CO2 gas, and this is actually going to produce then C2H2 gas plus 5 halves O2 gas. So when I do that, my delta H sign changes, and it's going to become positive 1299.6 kilojoules. Oops. Pretend like that didn't come up there. There we go. Where's my 6? There it is, 6. All right. Then the second reaction, I have carbon on the reactant side, but I actually want 2 moles of carbon, so I'm going to double that. So I'm going to take and change this to 2 moles of carbon, reacting with 2 moles of oxygen gas to produce 2 moles of CO2 gas. And so my delta H becomes 2 times negative 393.5 kilojoules. And then taking a look at the third overall reaction, the only thing I can see is I've got 1 mole of hydrogen here, and I actually want that 1 mole there, so I'm going to leave this. So no change. Let's see if that gets me what I want. So I'm going to leave it, and we'll do H2 gas. Reacts with 1/2 O2 gas, producing H2O liquid. So let's see what we can cancel out. First of all, my water cancels out, reactant side and product side. 2 CO2 on reactant side and product side. Let's see what else. I've got carbon, which is good. I've got my hydrogen, which is good. The oxygen is kind of interesting. I have 5 halves O2 here. This is really, if I wanted to change this, I could call this 4 halves. 4 half plus 1 half is 5 halves. So that actually cancels out here and here as well. And so let's bring everything that I have left over down. That gives me 2 moles of carbon and 1 mole of hydrogen gas, producing 1 mole of C2H2 gas, which looks good to me. So I did not change the enthalpy for this reaction, this last one, so that says negative 285.8 kilojoules, no change. So now all you do is you add these together, and hopefully when you add them together, you end up with a positive 226.8 kilojoules, which means that overall reaction is actually endothermic. It's going to take more energy to get that reaction to go than what it actually produces. So take some time, go back over these 2 examples, and take a look at your problem set, see what you can do with it.